This video covers optical fiber as a telecommunication transmission medium. We will discuss concept of optical fiber communication, fiber optic applications, basic optical fiber communication system, the structure of an optical fiber, principle of operation, advantage of optical fiber communication, characteristics of optical fiber, windows in fiber optic. We will also review loss characteristics, dispersion, bandwidth length product, electrical and optical bandwidth, various fiber types, cable construction, and ITU-T-compliant fibers. An optical fiber is a flexible, transparent waveguide used to transmit light. It is widely used in fiber optic communications because it allows transmission over longer distances, at higher bandwidths, with less signal loss, and is immune to electromagnetic interference. Optical fiber applications are numerous, ranging from global networks to desktop computers and involving the transmission of voice, data, or video. Key applications include long-distance communication backbones, video transmission, and computer data communication. One major advantage of optical fiber is its wider bandwidth. The information carrying capacity is greater than conventional systems, with the optical carrier frequency being significantly higher than radio or microwave frequencies. Another advantage is low transmission loss, utilizing ultra-low loss fibers and optical amplifiers. This allows for a repeater spacing of over 100 kilometers with minimal signal distortion, as amplification is done in the optical domain. Optical fibers are dielectric waveguides made from silica, an electrical insulator. This means they are not affected by electromagnetic waves, high current, or interference from power cables, providing resistance to crosstalk. Optical fiber communication offers high signal security since the transmitted signal does not radiate and is difficult to tap. Furthermore, the small size and weight of fiber optic cables offer advantages in storage, handling, and installation. Optical fiber transmits information, such as voice, data, or video, in the form of light. The process involves encoding information into electrical signals, converting them to light, transmitting the light down the fiber, detecting it, and decoding the electrical signals back into information. This diagram illustrates the key steps in optical communication, showing the conversion between electrical signals and light pulses for transmission and reception. The operation principle involves the behavior of light as it travels through different materials. When light moves from one medium to another, its speed changes, leading to a change in direction called refraction. The basics of light propagation can be discussed with the use of geometric optics. The basic law of light guidance is Snell's law. Consider two dielectric media with different refractive indices and with N1 greater than N2, and that are in perfect contact as shown in Figure B. At the interface between the two dielectrics, the incident and refracted rays satisfy Snell's law of refraction, that is N1 sine phi 1 equals N2 sine phi 2. In addition to the refracted ray, there is a small amount of reflected light in the medium with refractive index N1. Because N1 greater than N2, then always phi 2 greater than phi 1. As the angle of the incident ray increases, there is an angle at which the refracted ray emerges parallel to the interface between the two dielectrics. This angle is referred to as the critical angle, phi crit, and from Snell's law is given by sine phi crit equals N2/N1. If the angle of incidence increases A more than the critical angle, the light is totally reflected back into the first material so that it does not enter the second material. The angle of incidence and reflection are equal, and it is called total internal reflection. Light propagation through a fiber relies on total internal reflection. The fiber has a core and a cladding, with the core having a slightly higher refractive index. This causes light injected at an angle greater than the critical angle to reflect and travel down the core. The light continues to zigzag down the fiber's length through successive total internal reflections. Light striking the interface at less than the critical angle is lost in the cladding, where it is quickly attenuated. The characteristics of light propagation are influenced by several factors: the size of the fiber, its composition, and the light injected into it. Optical fiber utilizes specific wavelength bands for operation, including the O band, E band, S band, C band, L band, and U band, each with distinct wavelength ranges and typical applications. An operational window is the range of wavelengths where a fiber performs optimally. Typical operational wavelengths are 850 nanometers for the first window and 1310 and 1550 nanometers for subsequent windows. Optical fibers have a simple structure: a core and cladding made of high-purity silica glass. The core has a slightly higher refractive index than the cladding, enabling the fiber to guide light. A protective coating is also present. Fiber sizes are defined by the core size followed by the cladding size. For example, 50/125 means a 50 micrometer core and a 125 micrometer cladding. Different core and cladding sizes are manufactured for various applications. Attenuation in optical fiber is the loss of light signal strength. Intrinsic factors include absorption, caused by impurities, and scattering, such as Rayleigh scattering, which deflects light rays. Rayleigh scattering limits the use of short wavelengths below 800 nanometers. Attenuation from absorption is due to the inherent properties of the glass material, impurities, and atomic defects. The primary factors influencing attenuation are the fiber length and the wavelength of light. This figure illustrates how Rayleigh scattering, intrinsic absorption, and total attenuation vary with wavelength. Extrinsic attenuation is caused by external sources, such as macrobending and microbending. Macrobending is a sharp bend, while microbending involves small, often unseen, bends in the fiber. Attenuation is measured in decibels, or dB. Dispersion is the spreading of the light pulse as it travels, which can cause signal overlapping and limit the fiber's information capacity or bandwidth. Dispersion categories include intermodal delay, intramodal dispersion, material dispersion, and waveguide dispersion. This image visually represents the concept of pulse spreading, or dispersion, as the light signal travels down the optical fiber. Bandwidth is dependent on fiber length, often expressed as the bandwidth length product. Electrical bandwidth and optical bandwidth are related parameters, with electrical bandwidth being approximately 70.7% of the optical bandwidth. It is important to understand that electrical and optical bandwidth are simply two ways to describe the same system's capacity. For instance, a 10 MHz optical bandwidth implies a 7.07 MHz electrical bandwidth. Optical fibers are classified as step index or graded index. Step index fibers have a uniform core index, while graded index fibers have a non-uniform core with the highest index at the center. This classification yields three fiber types: multimode step index, multimode graded index, and single-mode step index. This diagram illustrates the three main types of optical fibers: multimode step index, multimode graded index, and single-mode step index, showing the structure of the core and cladding in each. Optical cables come in two basic designs: tight buffer tube cable, primarily used inside buildings, and loose buffer tube cable, which is common in outside plant installations. The International Telecommunication Union Telecommunication Standardization Sector, or ITUT, defines several compliant fiber types, including G.651 for multimode, and various single-mode standards for dispersion-shifted and bend-insensitive fibers.